So let me start by saying a few words about myself. This is a very special event for me because Shichi was my first student. It's the first student that I graduated. And literally, we haven't worked together since he graduated. This is the first time since then. Is that right? It's the first time since he graduated that I'm actually at an event that he's organizing, or he's at an event that I'm organizing, or we're doing anything whatsoever together.
Honestly, you reject many of my invitations.
I'm blissfully unaware. In that sense, it's something very special. And so I'm going to use this to shamelessly pitch collaboration. Because I'd like this not to be the last time for the next, how many years? I'm not even going to count, but I'd like to do more together. And so what I'm going to talk about is I'm going to introduce the San Diego Supercomputer Center in 2 slides, and then give you a little bit of a sense of what we do in AI from a quote unquote machine perspective and project perspective, and then talk a little bit about what I think we could do together, and then you guys can figure out whether I totally missed the mark. So the San Diego Supercomputer's mission, as I understand, is translating innovation to practice. What I mean by this is that SDSC adopts and partners on innovations from industry and academia across a wide range of technical things, anything that has anything to do with cyber infrastructure to first order, and anything that is in any way, shape, or form related to cyber infrastructure. And you can sort of list on the slide the kinds of things that I consider as that. And I like to claim that we're globally renowned for being a practitioner of this translation of innovation into practice. We're basically trying to pick interesting things that are on the verge of being applied, and then apply them and figure out how to make the most out of these technologies and hardware and software. Then I'm a physicist. I like to think in numbers. So I'd like to think about SDSC, the institute that I am the director of, in terms of numbers. And I like to think of them in terms of numbers on 2 dimensions. The top row is people, and the bottom row is systems. We have about 250 plus employees. We train about 3,000 people a year. That means about 3,000 people attend our training events. There's about more than 30 a year and they cover pretty much anything that you can imagine that is in any way, shape, or form relevant to software and computing. Then we have about 10,000 active Unix accounts on our high-performance computing system. So the big computing systems, the workhorse of SDSC, has roughly 10,000 active accounts. There's about 1 million plus users on our science gateways. In fact, we have one science gateway that has 2 million visitors a year. It's the NanoHub gateway. And we've taught about 1 million plus students in aggregate over the years in our Coursera courses. We run a big data Coursera course for some time now, and the totality of students that went through this is about 1 million plus. Then on the system side, we have 4 HPC systems inside the data center. It's about 200,000 x86 cores, about 1,500 GPUs or so. And then one system that I'll talk more about is a system dedicated to machine learning. That system can, to first order, not be used for anything other than machine learning. And I'll explain later what that is about. We have a universal scale storage system that is open for business from anything between 200 terabytes to tens of petabytes. So anybody can come and give us a credit card, and we give you storage, in essence. And then finally, we operate globally federated cyber infrastructure across 100 plus institutions on 5 continents. We run a content delivery system think of it as the data federation, whatever you want, that has caches in the network backbone on 5 continents, literally. We run this for LIGO mostly. They were the driver of it, but at this point, it's used by Dune, it's used by all kinds of customers. So let me switch to, and I can tell you more about these kinds of systems if you ask me in the break. I'm focusing today only on machine learning, and I split it up into training and inference because that seems the obvious split. And so I want to talk about the systems we have for machine learning training, Voyager, NRP, and Expanse, and start with Voyager. Voyager is, and Javier, who's sitting here somewhere, voila, is a co-PI of that system. And you can ask him on what it's like to run on it, or you can ask his students what it's like to run on it. And the idea is that it's totally architected for machine learning. And so what you're looking at is, you're looking at, does this work? So let me do it this way, because then the externals can also see. There is a single chip, a Gaudi chip from Habana Intel, is designed to have massive I/O capabilities to suck in all the data that you want to train on. And this includes, it's a 32 gigabyte of HBM, and then terabit per second I/O off the chip. The chip is then 8 of them integrated into a node, and the node itself has 6 times 400G to the switch. So you're literally running at 2.4 terabit per second into the switching architecture, where then all 42 nodes in Voyager have non-blocking transfer between each other at that kind of speed. So it's basically a monster of networking technology with lots and lots of compute, and the compute is entirely around machine learning. In fact, if you look at the user interface isn't your usual Unix prompt. It's actually a PyTorch and TensorFlow. And so you can ask Xavier and students for what it's like to use this, and I won't go into more details than that, because in fact, I actually don't know much more details than that. I've never used it. Another system that I know a lot more about, because I'm the PI of, is the National Research Platform. This is a system that was just recently funded, and a year ago, but it's only now being deployed. As usual, it took a while to actually get vendors to give you some hardware. And so the system itself includes a national data distribution network. What you see here, these circles, at the center of every one of these circles is a cache, and 3 of the centers is actually hardware in data centers. Nebraska and Massachusetts have 144 A10s, and therefore optimized around FP32 computing. Most of the core constituency that has used the previous infrastructure, the Pacific Research Platform, is basically CS folks who do AI, machine learning. So it's in a funny way an infrastructure that comes from machine learning with IceCube mopping up whatever is leftovers, and is now exploring other domains. At SDSC, we then have a high performance partition, which is a little bit more esoteric hardware. It includes 32 Xilinx U55C for ML inference, and I'll talk more about this in a second. And then it also includes 8 NVIDIA DGXs with 8 A100 80 gig each. So it's basically allowing you to do conventional, so AI on a conventional hardware platform, meaning NVIDIA. And the project is both a funded project and a community, in that we have a bring your own resources program. That means that you can buy hardware and we run it for you. And we run it for you, if you wish so, all the way from IPMI up. Meaning you don't even have to be responsible for the operating system. You're responsible only for plugging it in, providing power, providing a networking, and that's it. And then we take over via IPMI, install everything and maintain everything. And at this point, we have, or let's say at the end of 2022, when everything is installed and commissioned, we will have about more than 1,000 GPUs of all kinds. Literally anything from gaming GPUs, all the way from 1080 Ti's that haven't broken yet, despite the fact that they're old, to 3090s, and then of course some A100s, a fair number of A100s, etc., and A10s and so forth. The other thing that NRP comes with is a data infrastructure model. It comes with a model for storage, where that sort of tries to bring the best of a PRP and OSG together, meaning it has the notion of regional Ceph infrastructures. So you can come literally with a box that has storage on it and join our Ceph pool, and we integrate it via Rook. And then we have these regional Ceph pools. All of the regional Ceph pools will be origins of the data federation, and there is caching infrastructure in the backbone, and including in Europe. We are getting 2 caches, one in London and one in Amsterdam, that are fairly large and are at ESNet POPs. We right now have caches in Amsterdam, the Czechoslovakia, Italy, UK, Korea, and I believe there's one in Australia. So it's a very, very distributed data infrastructure. And the notion that we are introducing with NRP is that if I ask myself, and I want to work in such an environment, I might want to actually have the namespace that I own distributed into different locations where I have regional storage pools. And that kind of functionality, so that I can say directory foo goes to the East Coast, directory bar goes to the West Coast, that kind of thing we're going to develop and provide in the future. So that's it for training. Then inference, I want to talk a little bit about a specific type of inference that I believe was at least in your proposal. I'm not sure whether it is still survived. The buzzwords is either inference as a service or Sonic or whatever you want to call it. And what I'd like to point out that you could do this, SDSC is almost ideal to do this, because there is our HPC workhorse called Expanse, which is at this point 16 racks of mostly CPUs. There is about, and I've given you here some of the characteristics. It is NSF owned hardware that is allocated by an NSF mechanism. It is our own hardware that is allocated by you paying money, mostly for industry collaborations with academia. And then there is high throughput computing, 2 racks for high throughput computing that you access via path. And those racks are particularly interesting. It's 14,000 cores because you can get their, in essence, allocations for free. Meaning all you have to do is you have to have an NSF award from pretty much any NSF branch, any directorate, and you have to send a one-pager to your program manager. The program manager says yes, and voila, off you get an allocation that we manage. And so it's a very low bar to jump over. So Shichi could go there, send a one-pager or two-pager on what he wants to do, say, I want 1 million hours in order to commission a Sonic or whatever you call it, and I want to use Expanse path hardware for CPUs, and I want NRP FPGAs, and the 2 of them are in the same data center. Therefore, the kind of issues that I've read about in papers of yours of I/O is a non-issue, because we support terabit per second and plus networking inside the data center. So NRP is the first NSF machine that actually, if you just count, has 6.5 terabit of I/O into the system, because it has 32 FPGAs, each one of which has 2 times 100 on board, and we're hooking them all up eventually. Right now, there only a few are getting hooked up. So eventually they will be all hooked up. The top of rack switch is a 400 gig switch, and that switch is then connected to the rest of the infrastructure at SDSC at multiple 400. And so in principle, we can connect anything and everything in the building up to a terabit. Then in addition, we are just now receiving in fact, we just sent a 400 gig switch into the LA POP. Caltech and UCSD, basically Caltech and SDSC, Harvey and I will own a 400 gig switch at the LA POP that will be managed by our network provider in order to peer with anybody and everybody who wants at terabit and beyond. Scenic is giving me a connectivity at 400G this fall, initially only layer 2, from LA to San Diego, And whenever they can switch this at layer 3, it will become available to peer with anybody. In particular, Fabric, which is a terabit that will hit Los Angeles and connect from Los Angeles via, I want to say, Utah, Denver, Utah, Chicago to New York, where in New York it connects at multiple hundred to CERN, effectively. So bottom line, you can do a fair amount of wide area network connectivity into this system. You can have jobs run at the tier 2 centers on Caltech or UCSD and connect into it. There is lots of opportunities to do FPGA, to do inference as a service. Bottom line, my pitch is that SDSC is the perfect playground for scaling out Sonic or whatever you call it these days and the like, and do it at say 10,000 cores and hitting 10,000 cores into multiple FPGAs, of which we have 32 of. But also you can just use those FPGAs for whatever else you want. They're going to be available. The allocation strategy is you send us an email and I say yes, basically. Because for the first 3 years of this project, the PI owns the entire machine. It's a test bed in NSF speak. And we then have to do what you do and convince the NSF that we're worth it. And I hope that you help me convince the NSF that we're worth it. That's all I had. Thank you very much. Questions?
Questions? All right, I'll start. I'll start with the end. So you have these FPGAs. Do they have, the big thing about FPGAs or doing like ultra high throughput is that you can just go from FPGA to FPGA to FPGA without going through PCIe. They all have network ports, right?
So I think we haven't bought enough network cable to cable them all up, but and I don't know how many are going to be cabled up on day one, but they will all be cabled up eventually. The switching infrastructure is 32 400 gig ports. And so that means in order to hook them all up, we need 16 ports on that switch. I'm willing to spend 16 ports. The cables, there are these octopus cables that are 400G at one side and 4 100s on the other. So you would effectively run 2 FPGAs into one switch port on the switch. And then you can go via the switch, which is fully non-blocking and P4 programmable. So you could even do arrangements where you isolate traffic to only go between the FPGAs if you wanted to. So bottom line, yes, I had told you initially when we wrote the proposal that the answer would be no, but the 400 gig switches have become so cheap that we've basically bought one of those, and it's part of we're doing some R&D on software-defined networking across the wide area network inside the data center. And so we bought this switch in order to enable this and play with P4, play with the FPGAs. So literally you can do anything you want. You do not have to touch PCIs. Where you might want to touch the PCI bus is that same system, all the FPGAs are plugged into the PCI bus, and then the PCI bus has 350 terabyte of NVMe. If you wanted to have really large volumes of data in the back and access that via the FPGA in some funny, interesting way, that you would have to use the PCI, because it probably would be a little bit weird to go out of the Ethernet, come back into the Ethernet, mount it on another device. We could do that too, but maybe at that point you might be better off. Anyway, yeah, whichever. You get the idea.
All right, other questions?
You have one from Zoom, Phil.
Oh yeah, Eric, do you have a question? Sorry.
Yeah, hi, Frank. This is Eric Katsavanidis. Thanks for this, and congrats actually for the center that you're running. 2 quick questions. What is a typical duty cycle, or maybe time average? What fraction of this resource is generally available? And the other thing that I was about to ask, or maybe you answered it, is how we can get access to it. And you've hinted that we can just email you, but be careful what you wish for on that. So can you say a few words as to the availability as well as the process?
So the easiest, so there is first off, this is a little bit of an experimental system, as you can probably imagine. And so we're sort of making this up somewhat as we speak. There is most of the infrastructure, and eventually all of it is available via Kubernetes access. And so you can just get accounts on the Kubernetes infrastructure with access to namespaces in the usual way. That's one thing. And there'll be a website where you can request account access and so forth. And then you have a license to kill, so to speak, and just compete. Now, for the FPGAs, we're very likely to make this a little bit more human in the loop. And because I don't think that we have the means to schedule the FPGAs on day one. And so right now, my biggest fear is that the FPGAs are permanently empty. And so I'm not worried about that part of the system. For all of the GPUs, I suspect that the A100s will be busy almost all the time. So that'll be hard to get cycles on. Whereas on the various other GPUs, or in the past, you can ask Benedict, they basically have mopped up whatever was available and have often had anywhere between tens to hundreds of GPUs at a time. And so the community that's on there is a significant fraction of it is just people who want to have interactive access and do this via kubectl or via Jupyter notebooks. And then there is a batched back end to it via OSG, where people literally mop up whatever is left. I don't expect for the first year there to be a whole lot of contention, and especially the FPGAs. My biggest worry is that I need to find customers. In the proposal, we had, I think, five-ish different people who expressed interest, Phil being one of them. And how many of those will really use it? And it was all over the place. It was the kind of stuff that you guys do, but also there were people who wanted to do molecular dynamics in simulations in FPGAs, following the idea of Anton 2 in a way. And then there is one of the co-PIs is Tajana Rosing, and she is a professor in computer science at UCSD, and she specializes on doing anything and everything on FPGAs. She basically ports things to FPGAs. We have now a COVID-related gene sequencing workflow that runs on FPGAs. Think of it as the mental analog being in what's it called? The gene sequencing company from San Diego offers you an ASIC, a Dragon. You can sort of do stuff like that on the machine. But bottom line, I think it's going to be empty a lot for the time being on the FPGAs. Does that answer your question?
Thank you. Good.
All right, are there other questions? All right, if not, let's thank Frank again.